Okay, this is the video for 8.6 Improper Integrals Day 1. And I wanted to start the video with number 13 from 8.5. Alright, and 8.5 is when we got this, partial fraction stuff going on here. Okay, and do you guys agree that this is not a proper fraction? So, what are we going to do? Well, let's do our long division to get into the form that we can use right here. So I'm going to divide the x squared by x squared plus 9 to get first term of the quotient as 1. And that would give me an x squared plus 9. And if I subtract these two polynomials, I'm going to be left with a negative 9. Alright, so what do we got right here? We got our quotient 1 plus our remainder, which is negative 9, minus 9, over our divisor, x squared plus 9. So let's put this together, and we get the antiderivative of 1, differential of x, minus 9, and then the antiderivative of the differential of x over x squared plus 9. Okay, let's start solving this baby right here. So I'm going to go, well, the antiderivative of the differential of x is just an x minus, and now I'm looking at this and thinking, okay, here's where I typically do my substitution or my improper integral and stuff like that. And let's see though. Ooh. Do you see that x squared plus 9 right there? You know what I'm thinking? That's right. The antiderivative of the differential of x over x squared plus 1 is inverse tangent of x plus the c right there. Alright? So we're going to manipulate this divisor. So instead of an x squared plus 1, we're going to have, or instead of an x squared plus 9, we're going to have a u squared plus 1. Alright, so here's what I'm going to do. I'm going to make that 9 right there a 1. So, what do I want? 9 over 9. Which means I had better divide this first term in my divisor by 9 as well. So I'm going to write that in x to the third quantity squared. Just like that. And now what I've done is I've taken my divisor and divided every term by 9, which means I multiplied the entire integrand by 9. Alright, yep, look at that right there. Okay, so see that factor of 9? Well, when I do this, I'm going to have to take care of my substitution here, so let's do it like this. Okay, so I've got x minus, okay, and I'm going to now make my u x over 3, and my differential of u then would be a 1/3 dx. Right there. Okay, so let's put everything now in terms of u's right here. So I've got the u squared plus 1 right there. Okay, very cool. All right, and now let's see what we got here. I put in my differential of u, and that gives him my 1/3 differential of x right there. All right, so what I'm going to do is take that 9, and the 1/3 came out. Okay, so that's a 3 right there. Plus c sub 1. And now look at what we have. U equals, there's my x, there's my minus 3, and I've got an inverse tangent of u, which is that x over 3, plus the c. And there's my answer, number 13. Pretty cool problem. A little different than most of your example problems. That's why I wanted to share it with you guys. Okay, now 8.6. Wow, there's a lot of key points right here. So instead of spending 20 minutes going over every key point right here, let's just make sure these are put clearly into this lesson. And let's move on to improper integrals. So improper integrals. The definite integrals we have studied so far represent signed areas of bounded regions. Oh, this is so cool. You're going to love this. So here we go. This is a definite integral, and the answer to a definite integral is an area under a curve. It's just a number. Okay, so this area under this curve right here is approximately 21.2000 or 00. Okay, so there we go. There's your typical definite integral. Now, let's take a look at this one over here. What if I found this area? What if I went the definite integral from 0 to 1? All right. Do you notice that that's unbounded right there? Because I have a vertical asymptote at x equals 0. So the question is, if that's unbounded, would that area be infinite? We're about to discover some really, really cool things. Okay. Areas of unbounded regions also arise in applications and are represented by improper integrals. There are two ways an integral can be improper. One or both bounds may be infinite. So something like this. The integral from negative infinity to a of f of x dx. Or the integral from a to infinity of f of x dx. Or both bounds could be infinity. The integral from negative infinity to infinity of f of x dx. 2. The integrand may tend to infinity or 0, just like we saw on that last picture when I talked about x approaching 0 from the right, and we were approaching infinity. All right, so let's take a look at this now right here. Okay, the integral from 0 to 2 of the differential of x over x right there. Okay, so what does this 1 over x look like? There it is right there, right? So that's y equals 1 over x right there. And notice, as x is approaching 0 from the right, I'm unbounded. And also, by the way, as x is approaching infinity, I'm also unbounded. So, what is the limit as x approaches 0 from the right of f of x? I hope you all agree that's an infinity. Now, what if my bounds were changed and I was going from 1 to infinity? What is the limit of f of x as x approaches infinity? Well, that's approaching 0, isn't it? All right. These are unbounded, all right, because we can never reach x equals 0, and we can never reach, going the other way, y equals 0. Right, here's another example, the bell-shaped curve, y equals e to the negative x squared over 2. All right. As x approaches negative infinity, or x approaches positive infinity, we're never going to get to that x-axis. Okay, so this is a situation like this right here. Okay, bell-shaped curve. The region extends infinitely far in both directions, but the total area is, and I think we're going to discover the total area of this bell-shaped curve down the road here. But for right now, I think I'm just going to call it finite. Interesting, huh? So how could an unbounded region be an infinite area? Or I said that wrong. How could an unbounded region give me a finite area? That questioned mathematicians for a lot of years. So, how can an unbounded region have finite area? I'm sorry I'm laughing a little much. You know, I am heavily medicated right now, okay? So, everything just seems funny and cute. Hope I can still do a calculus. To answer this question, we must specify what we mean by the area of an unbounded region. Okay, consider the area under the graph of f of x equals e to the negative x over the finite interval 0 to r. That's a closed interval right there. So here's my curve, y equals e to the negative x. And my lower bound is 0, my upper bound is r right there. All right? I don't know, that area there looks pretty finite to me. Okay? So let's figure what this would be right here. All right. Now, I hope you guys to the point where you can give me the antiderivative of e to the negative x as negative e to the negative x immediately. Just like that. All right. And if you don't remember that, you get that through substitution. I'll put that over here. There it is right here. Your u is negative x. Your differential of u is negative dx. And works out every time. You're going to use that a lot, so you'll have that memorized right there. Remember, the antiderivative of e to the negative x is negative e to the negative x because of substitution. All right? And you know me, most of the time I don't like to have a negative in front of this, so I bet you I drop the negative and I flip my bounds. That's old school, isn't it, right there? All right? Now, is it time for the fundamental thermocalculus? Well, I've got an e to the opposite of a number approaching 0, okay? E to the 0 is 1. And then I've got an e to the negative r, or I could write that as 1 over e to the r if I wanted to. I'm going to leave it like that for right now. Okay? So let's think about this now. So we're saying that this area is finite, and it is exactly 1 minus e to the negative r power. Bam. Okay. As r approaches infinity, this area approaches a, and I think we're going to say that's a finite value right there, but you feel it closely, that's going to be an unbounded region right there because we're never going to get to the x-axis. So let's show it right here. So I'm going to go 0 to infinity of e to the negative x differential of x. Okay, infinity. Okay, it's an improper integral. As soon as you see a bound that's infinity or negative infinity, you know your integral is improper. So we're going to do this like this. We're always going to call that bound approaching infinity r, and then all we have to do is take the limit as r approaches infinity. So we're going to find this definite integral right here and then apply the limit. And here's what we're getting here. Okay, so what is that? I'm curious. Well, that's going to be the limit as r approaches infinity. And don't forget, what is the antiderivative of e to the negative x? Negative e to the negative x. Okay? Yep. Oh, and I'm going to go ahead and we already solved that up there, didn't we? So I can put in that 1 minus e to the negative r right there. All right? And now, think about what this is approaching right here. 1's constant minus e to the negative r, where r is approaching infinity. Well, isn't that e to the negative x? As x is approaching infinity, isn't that approaching 0? So that's just a 0, and I've got a 1 right there. Okay? Excuse me, I've got my iPad going crazy in the background, and I can't quite reach it. I'm just going to let it go for now, okay? All right, and there we go. So, guess what? This unbounded region has an area of exactly, believe it or not, 1 square unit. Wow. So, the area approaches a finite value. Isn't that amazing right there? Okay, it seems reasonable to take this limit as the definition of the area under the graph over the infinite interval, the half-closed interval from 0 to infinity. Thus, the unbounded region has area of 1. 1 square unit. Amazing. Okay, so here's your definition. Improper integral. Assume that f of x is integrable over the closed interval from a to b for all b greater than a. The improper integral of f of x over the half-closed interval from a to infinity is defined as the following limit if it exists. So here we go. We're going to infinity right there. And we don't like that bound of infinity, so we're going to have to make it an r and simply say we're going to do the limit as r approaches infinity. There it is right there. We say that the improper integral converges if the limit exists and is finite, and that it diverges if the limit does not exist. So convergence versus divergence. This is so cool. Similarly, we defined, all right, here now my lower bound is approaching negative infinity. So we're going to do the same thing. We've got to approach a number, so we're going to call that r, and do the limit as r approaches negative infinity. A doubly infinite improper integral is defined as a sum provided that both integrals on the right converge. So if we get this one right here, we're just going to do the sum of two integrals. And I'm going to go from negative infinity to 0 on the left. And then I'm going to go from 0 to infinity on the right. Now, obviously, this number could be any number besides 0, but why not make things as simple as possible? All right, so, hey, it is our first problem. Show that the improper integral from 2 to infinity of the differential of x over x cubed converges, and compute its value. All right, so here we go. Now I want this to be really automatic for you guys right here. You see that infinity? You know that your bounds need to be numbers. Infinity is not a number, it's a concept. That makes this improper. Yeah, so I'm going to call that r, where r is some real number, and we're just going to do the limit as r approaches infinity. Like that, okay. Now here we go. So that's going to be the limit as r approaches infinity of, now I have, that's an x to the negative 3, right? So the antiderivative of x to the negative 3 would be x to the negative 2 divided by negative 2, which I could bring out as a negative 1/2. And I'm going to go lower bound of 2, upper bound of r. All right, so let's go. 1/2 the limit as r approaches infinity of x to the negative 2. Oh, look at that. I just dropped my negative out front. So now I'm going to go from r to 2. Didn't have to do that, but I love getting rid of negatives whenever I can. So this is going to be, well, 1/2 of the limit as r approaches infinity of fundamental theorem of calculus right here. F of b would be 2 to the negative 2, which is 1/4. And then f of a minus f of a would be r to the negative 2, or 1 over r squared if you like to see it like that. And I know I like to see this like that, because isn't r approaching infinity? So 1 over r squared would be approaching 0, giving me a 1/4 times a 1/2, and my answer is 1/8. We just did it. Isn't that cool? We just showed it converges, and we even computed its value. So this area right here is 1/8 of a square unit. Unbounded region, all right, with finite area. And that's a small number right there too. Wow. All right. Looks like the same situation, doesn't it? Determine whether the improper integral from negative infinity to negative 1 of the differential of x over x converges. So let's do the same thing. We don't have any questions. We're in great shape. I'm going to make that negative infinity a bound of r, and then do the limit as that r approaches negative infinity. Just 1 second. I am so sorry. Okay, can you guys give me just about 30 seconds here to take care of some important stuff in real life? Oh man, did I just say that? I'm talking about now school and making these videos. Did that sound like that's not real life? Don't take that personally, you guys. You guys are real life and some of the most important things in my life. Okay, got it going here. So, well, I'm glad you guys all know what the antiderivative of 1 over x is. Isn't that going to be what? The natural log of, and will we need an absolute value? I believe we will. Absolute value of x. Okay, and now let's put in our bounds. So we're going to go from r to negative 1. Okay, that looks really clean right there. All right, equals, well, let's go to the limit as r approaches negative infinity of fundamental theorem of calculus right here. the natural log of the absolute value of -1 would be the natural log of 1, and the natural log of 1 is a 0. And then I've got the natural log of the absolute value of my r. Now r is approaching -infinity, so I'm getting negative the natural log of something approaching infinity, and that's going to be infinity, so this is going to be negative infinity. Wow, notice that. We had an unbounded region, and then we had an infinite area. The area diverged to negative infinity. Okay. Conceptual insight. This is important right here now. Make sure you understand this. If you compare the unbounded region, shaded regions in the last two examples, okay, looks like we have the same situation, doesn't it? Okay, so this one was finite, it was 1/8, and this one diverged to negative infinity. Wow, they don't look very different. What's going on? You may wonder why one has finite area and the other has infinite area. Yep, we're wondering. Convergence of an improper integral depends on how rapidly the function f of x, that integrand, tends to 0 as x approaches infinity or x is approaching negative infinity. So for the 1 over x to the third, that function is approaching 0 fast enough for convergence. Wow. See this 1 over x? Where did I go here? What's this one right here? Okay. Yeah. All right. From now this is definitely approaching 0, but it's not approaching fast enough for convergence. This one diverges, this one converges, and it converges to 1 over 8. So our calculations show that x to the -3 decreases rapidly enough for convergence, whereas x to the -1 does not. So an improper integral of a power function, f of x equals x to the -p. Oh, we gotta love these. These are called p integrals right here. Okay? And you might see it in this form, x to the -p, or obviously 1 over x to the p. They're still p integrals. Note that f of x equals x to the -p decreases more rapidly as p gets larger. Makes sense, you guys? Interestingly, our next theorem shows that the exponent p equals, and what's the big divisor? It's a 1. P equals 1 is the dividing line between convergence and divergence. So here we go right here. Theorem 1. The p integral over the half-closed interval from a to infinity for a greater than 0. All right? We've got the integral from a to infinity of the differential of x over x to the p equals, and it is finite if p is greater than 1, like the x to the third we saw earlier, and it will actually go to this expression right here. My lower bound a to the 1 minus p power over p minus 1, or if p is less than or equal to 1, is simply what? Diverges. Okay, so there it is. Let's check this with the one that we just got as a 1 over 8. All right, so here we go. What's p equal here? Well, p equals 3. And so my a is a 2. So I'm going to go the limit as r approaches infinity of the integral from 2 to r of the differential f over x to the third converges to. So I'm going to go 2 to the 1 minus 3 power, that'd be a 2 to the -2 power, over 3 minus 1 over 2. And isn't that 1 over 2 squared times 2? 1/8. 1/8. There it is. So, you have a rule for this situation right here, and you can just do the arithmetic if you'd rather not do the improper integral. Now, I'm hoping you guys get to the point where you think solving improper integrals are so easy that you just as soon do that as to apply this formula. But You can go your own way. Many roads to the ultimate reality. Yeah. I can't read that. I hope you can. Must be brilliant, though. All right. Here's our next problem right here now. I hope you guys are having fun. Hey, what's the deal here? This is integrating with two factors. All right. So I don't know why. My iPad's going crazy. All right. But in the back of my mind, I'm hearing a band called The Who singing, "Who are you? Who are you? Who? Don't pick on me, you guys. I'm almost retired. So here it is right here. I'm late. I'm going to let U equal X and my V prime equal e to the negative X. U equal X and V prime, that would be e to the negative X. This thing is very distracting. Let me just check things out. Oh, just people in my stupid game getting crazy. All right, let's go. So I've got x e to the negative x. So u prime would be, well, what's the absolute value of x? That's a 1. All right, and I told you you'd be doing this a lot here. What's the antiderivative of e to the negative x? Negative e to the negative x. All right, so let's go. Oh, so I need a uv. U is x. V is negative e to the negative x. Okay. Minus v e to the negative x. Okay. And then my dx. Oh, but that's a negative, so that's got to be a plus there, right? And then my differential of x right there. Okay. So let's go. So that's going to be fundamental thermocalculus right here. I'm going to go negative, and I've got an r, and then how about an e to the r right there? All right. And then the 0 goes in there. That's going to go to 0. And now I can do this antiderivative right here. So I'm going to go a negative e to the negative x again. Negative on the outside right there. And I'm going to go from 0 to r there. So I'm going to get a negative r over e to the r. And now I'm going to drop that negative and make it positive and reverse my bounds. R to 0. And that's going to be negative r e to the r. And then I've got a plus fundamental thermocalculus right here. E to the negative 0 is 1 minus e to the negative r. And I'm going to write my e to the negative r as 1 over e to the r. All right. Now, notice how I just did this antiderivative first. Okay. And I immediately just changed that infinity to an r right there. So now all I have to do is do the limit as r approaches infinity of this expression right here. Okay? Now, some of you can see this right now. All right? I'm thinking that, well, easy. R is approaching infinity. So this term's going to 0. And what has greater magnitude, r or e to the r? I'm going to say this is going to go to 0, and I'm going to end up with a 1 right there. But all you're doing is taking this limit as r approaches infinity of every term separately, just like that, and I'm hoping you're seeing a 0, a 1, and a 0. Why did I bring that out like that? Let's see. Oh, I'm just doing one term at a time here. Okay. There's my plus 1 right there. And that's going to be my 0 plus 1. And that's 1. Again, I'm just showing extra stuff here. I want you to be able to look at each term right here and come up with these. E to the r has greater magnitude than r, so this is going to approach 0. 1 is constant. And obviously e to the r has greater magnitude than 1, so this is going to approach 0. That's going to be a 1 right there. Hey, guess what? That's it. So, day 1, all right. You guys, let's do 5, 13, 15, 21, 35, 45, and 47. And if I were Malcolm, you know, you guys are seniors. Your teacher's at home in bed. Hopefully you did this video in one period. I don't know how Malcolm's doing it, but I'm sure he's doing a great job. And I would give you guys a day to work on these problems in class. Okay? So, have a great one. And I will close out this one and I'll start another video tomorrow. I love you all. Bye-bye.